doing? Okay, so we are starting. So I have a big pleasure to introduce Nilasis. Now it's problem how to pronounce this name. Chaudhuri? Tell it.
Chaudhuri, yeah.
Chaudhuri, very well, yeah, of course. And let me say that he did master thesis with Professor Maitili Ramaswamy in Tata Institute. Then he moved to Berlin and he did PhD thesis with Eduard Feiraiser. And then he moved to Imperial College as a postdoc. He's postdoc of Evelina Zatorska. And today he will speak about Navier Stokes Fourier system with Dirichlet boundary condition for temperature. So please.
Thank you, Sharka, for this nice invitation and giving me to talk in this Nečas continuum mechanics seminar. And it's my pleasure to try to introduce this problem and talk about it a little bit. Okay, so I am starting right now. So I will talk about the Navier Stokes Fourier system of, but this time it's with the Dirichlet boundary condition for temperature. Generally, the Navier Stokes Fourier system gives the heat conducting viscous fluid, and so you can see that it consists of three main equations. The first is the continuity equation, which is basically the mass balance, and then you have a momentum equation or the momentum balance, and then we consider something the internal energy equation. So here the rho stands for the density, u is the velocity, and the theta is the absolute temperature. So for the time being, we just consider these three as the independent state variables, whereas the other quantities, you see the pressure here, this P is the pressure, S is the viscous tensor, there is Q, which is the heat flux, and also there is this E, which is the internal energy. And all of these are function of rho, theta, or I will try to write down the explicit form of the viscous stress tensor later on. And here in general, the G is given by some external force. And this dx of u is basically the symmetric part of the gradient. Okay. So, so this is the system that we want to consider, and you already can see that there are like plenty of things and plenty of extra assumptions that we have to introduce. So the first relation that we want to introduce is called the Gibbs relation. So you see this the Gibbs relation, and it's given by that this d is the derivative with respect to rho, and the second one is with respect to temperature. And it is the relation between the pressure, the internal energy, and some other quantity, which is the S, which is the entropy. So before to that, we didn't introduce anything about the entropy, but eventually this is related by the pressure and the internal energy. And I told you I will consider the viscous stress tensor. So in this case, my viscous stress tensor depends on absolute temperature and the symmetric gradient of the velocity. So you see that the first part, which is given by this is basically the stressless part. And the next part is the divergence part, and mu is the shear viscosity coefficient, and eta is the bulk viscosity coefficient. One can consider very general form of this coefficient, but for the time being, I just only consider they are functions of the absolute temperature. The next thing is how the heat flux has been defined, and it's given by the Fourier law. And you see there is kappa, which is called the heat conductivity coefficient. And I will talk about some particular form because eventually our result depends on some particular structural hypothesis on this heat conductivity coefficient or all these coefficients like on that. But okay, so before going to that, so what we are interested in the Dirichlet boundary condition. Sorry, I just put so boundary conditions. So we consider a bounded regular domain. For time being, considered smooth domain, or at least it's a C3 up to the boundary. And we consider the non-homogeneous Dirichlet Dirichlet boundary condition for the temperature. So you see that there is a, if you consider any domain, so some temperature has been prescribed in the boundary. And for velocity, we just consider the zero boundary condition. Later, we will try to say that even for a very general setup, we are able to conclude something even for very general boundary conditions, which often referred in the literature as the open systems. And I will come to that after some point. Okay, so what it is related? So this problem is closely related to the Rayleigh-Bénard convection problem. So the problem in a simplified form, you can consider omega, which is a subset of a three-dimensional domain, where this is the torus, and this is this is the R2 direction, and this is the Z direction you can consider, which is just 0, 1. And you are in this torus times this 0, 1, where at the, sorry, it's a mistake. Yeah, so the bottom temperature and the upper temperature is given, and generally the bottom temperature is higher. So there is a convection of the flow. So it is quite well studied in the context of the incompressible fluid. But this problem actually now, the problem we are considering is basically the Rayleigh-Bénard convection problem. It's the compressible counterpart of it. So that's why this problem makes sense to consider for its historical significance and everything. Okay, so what is known? So from our existing literature, we can see that only the local in time strong solution for sufficiently regular initial data is known, and it's by Valli and Jankowski in 1986. But then also you can extend this for some small initial data. Then you can, if you have some smallness data, so then you can say also global in time for small initial data. But for a more general, like global in time solutions, nothing is known. So after the strong solution theory, then the weak solution theory came, and even though we cannot handle this kind of boundary temperature in the weak solution theory, even for the global in time case. So what is known for the global in time weak solution case is often referred as the no flux boundary condition. So either in a domain you consider this Q, and if you write down the form of Q, you can see that this is this type of condition. So in some other words, if you just consider this Neumann type boundary condition on temperature, this is basically the no flux, or even for simplicity, you can consider the torus. So there are two cases, either it can be torus or it can be like Neumann type boundary condition. For this global in time weak solution theory is known, and you can see from the pioneering work of Lyons and then Fereisel and Novotny, Bresch Desjardins, and then Melle-Vasseur, and very recently another work by Bresch and Jama. Obviously, like all these cases have some of their difficulties, some partial result, and then some additional structural hypothesis on this thing. But what I want to do, I just first quickly, after giving some thing about the hypothesis, I quickly come back to the weak formulation of this problem and from where the exact problem is happening, and our method to overcome this problem. So this is the first few times talk, and then we'll talk about a little bit on the existence theory. Okay, so these are some structural hypotheses that we have to assume in order to get some existence result even for our theory, or even these are the same structural hypotheses that mainly Fereisel, Novotny, or even Bresch Desjardins, or most of all of them take somehow similar type of hypothesis. Some minor modification has been achieved by Bresch and Jama very recently. So first thing is called the thermodynamic stability. So it somehow states that the pressure is monotone with respect to density, and the internal energy is monotone with respect to the temperature. And the next motivation is just the consideration of the pressure, what form of the pressure we consider. So it's generally divided into two parts, which some first part is called the molecular pressure, and the second part is the radiation pressure. And even in the molecular pressure, there are like two components mainly we consider. I think Milan is here. Milan will be very much like this rho theta plus rho power 5/3, which I also like, because all this extra assumption we will assume based on this thing. So the rho theta, it came from the ideal gas law or the Boyle's law. And then we need to add this quantity, which is called 0 Kelvin isothermal. So when the temperature is 0, still you are having some sort of some sort of density dependent factor. And the another important thing is consider the radiation pressure, which is given by the Stephen-Boltzmann law. So this is often referred as Stephen correction of the temperature. And so taking motivation from this pressure, we consider a very general form of pressure, which basically, like, you can say that if you, in this case, if you just consider this P of Z is 1 plus Z over, I think 5/3. Yeah, so then you can actually get back to this rho theta plus this quantity. Okay, so the purpose of considering very general pressure comes in the next slide. So in the next slide, first thing it has nothing to relate. We can consider following the Gibbs relation. For the entropy, we just recalculate things and we see that the entropy has this kind of particular form. And this particular form also helps us somehow to get assume another hypothesis, which is also called the third law of thermodynamics, which says that the entropy is going to 0 when the absolute temperature is going to 0. So this is the setup for our problem. And now I just want to go step by step. So for time being, for simplicity, I would suggest that if anyone has this hypothesis problem, just consider the pressure to be more particular form of this rho theta plus some constant times rho power 5/3. And that's basically gives us the main motivation. Okay, so let us put some more assumption, and these are the assumptions on the transport coefficients. So basically the bulk viscosity coefficient and the shear viscosity coefficient and the bulk viscosity coefficient has some power law kind of a thing. So for similarity, one can just start with mu rho is something like 1 plus theta, sorry, not mu rho, mu of theta is 1 plus theta. So it basically satisfies all these hypotheses. And if for eta theta, you can also consider the same thing. And the heat conductivity coefficient is somehow also similar. So for time being, one can just think something like 1 plus some theta power some beta, where beta is large. And we will come back to this quantity, and actually depending on some extra hypothesis we need, we have our desired results on that. Okay. So let's quickly go through that how the weak formulation, and this is for the no flux case. So that means you have the heat flux over the boundary is 0. So in this case, we want to just revisit the weak formulation that done by Lyons and Fereisel, Novotny, and all of them. So, okay, we have continuity equation, we have momentum equation, and we have an internal energy balance. These are 3 sets of equations that we have. Now what we do, we just multiply the momentum equation, and after some manipulation, we ended up in this equation, which is referred as the total energy balance. So this is the internal energy, and this quantity is the kinetic energy. So the kinetic energy balance is given by this set of equation. Now we use this fact that the flux is 0, and this gives us this particular identity: the total internal energy, the internal energy, and the kinetic energy. This, the time evolution of this is basically given only by the external forces. So if you, for simplicity, if you consider the Z to be 0, you can see that the total energy is conserved. And what another thing we consider, along with this 3 set of equation, we use our Gibbs relation. So this is due to Gibbs relation. So we know that Gibbs relation gives us some relation between the pressure, the internal energy, and the entropy. And this actually gives us something called entropy inequality. So we have to just replace this and use some renormalized version of continuity equation. So eventually we will end it up in this equation. And even more physical way, if one can consider this instead of inequality, one can consider the entropy inequality, which basically is a direct consequence of the second law of thermodynamics. So these things allows us to consider the following weak formulation. So this is basically, I took this weak formulation from the Fereisel and Novotony's book. So which says that, okay, the first weak formulation is the weak formulation of the continuity equation. So means you can multiply this by a smooth test function and put all the derivatives there. Obviously, the initial data has to satisfy in a certain sense. Similarly, you can do this for some momentum equation, and you have a total energy equality. So you see that for almost every tau, almost every point, you have the following equality. And you have the entropy inequality in some following weak sense. So this is for the conservative case or the no flux case, you can have the following weak formulation. Now, we want to have a weak formulation for our setup. So our setup is like not even Q. So our setup is theta is basically theta B on boundary. So that means like if you consider Q theta is given by minus some kappa theta times gradient of theta, and this Q theta dot n on boundary will be given by this function of theta beta and this something like that. Okay, so I will come to because we don't have this quantity. So what happened? So just to recall that what we do, we can again from these two, sorry, not these two set up this momentum equation and the internal energy balance. We do the same thing. We multiply the momentum equation by velocity and then add, we have the total energy balance. There is the first equation, there is no problem. Now, if you want to integrate it over time, you see now Q dot n is not 0, so you have some boundary term. And this actually allows us to get something like an extra estimate. So if you see that from the a priori estimate point of view for the no flux case, when you have this bound, clearly you get some a priori estimate out of this total energy equality. Whereas since presence of this boundary term locks us to get any getting any a priori estimate. Now, another thing we observe that what we do, we have the entropy inequality. So we multiply this by some sort of smooth extension of boundary. So you have a boundary data, which for the time being, we assume that this theta b can be smooth, and you consider something like some extension of this theta b, some smooth extension, and which is only fact that it has to be like strictly positive. I will come to that later. And another hypothesis we need here, it's like this theta b is strictly, sorry, this theta b is strictly positive. So what happened? Just let's see this term. So we are multiplying this quantity, divergence of Q theta times this function with this theta tilde. We can write it as divergence of Q theta times theta tilde minus Q over theta gradient of theta tilde. Now, if you see that in this term, if you want to integrate, we just integrate this term. I am not carrying anymore. So this term gives us, so this term actually like giving us something like Q theta tilde at boundary and divided by theta at boundary. So roughly on the d omega after the integration by part. And these two cancelled, obviously it's n. So you see that there is after doing this, you get this term here, which is basically the Q dot n. And surprisingly, it has exactly the opposite sign what we have in the total energy balance. So what we do, we just add these two things and see what happened. And so these are the two things. I just wrap up the whole thing, these two things, and we just add these two quantity. And we see that this gives one equation like that. And without any boundary terms, sorry, there is a mistake. It's everything is omega. So there is no boundary term there. So what happened? Okay, the kinetic energy is there, but instead of internal energy, we are having some quantity which is this rho e minus this theta tilde, which is the extension of the boundary value. So instead of getting one inequality, we are getting a set of inequalities. It depends on the extension, and this particular quantity in literature is called ballistic energy, which is termed by the Ericsson. And this inequality is called the ballistic energy inequality. So this motivates us to consider that instead of the weak formulation based on the energy inequality, this motivates us to consider the following weak formulation. Okay, what we consider the continuity equation in weak sense. We consider the momentum equation in weak sense. Then we consider this ballistic energy inequality for almost every t. So sorry, here there is, I made this mistake. There is no tau d. Everything is in omega. Sorry for this. And we have this ballistic energy inequality for this set of any extension. And this thing, we just add that the entropy inequality in distributional sense, because we see that if we just do the weak formulation of the entropy inequality, we can have some boundary term. But if we consider it for, for something like very no boundary, like we tested by some compactly supported function, we still get this entropy inequality in this distributional sense. So this is mainly these three is enough for us to consider the weak formulation of the problem. This we get like as a direct consequence of the weak formulation. Okay, so this gives us to define the definition of the weak formulation, weak solution of the problem. So what we say, we give the, so this, sorry, I didn't mention it earlier. This capital S is the rho times the small s, which is called the total entropy. And if you see from this equation, I'll just come back in a minute. So this rho S, this is actually the capital S, and this is also a conserved quantity. So we give all the initial data in the form of the conserved quantities. And okay, so what is our definition? So we have the weak formulation before. We need this density and the momentum in some C weak spaces because we have to justify the initial data. The velocity u is in some LP spaces. So for the time being, for simplicity, if you take gamma to B1, you just get this L to W1 to 0, L2 in time, W1 to 0 in space. And then the theta is the temperature, which is also in a very nice space because of this internal energy balance of some power. And some other regularity of this theta B and log theta will occur. Okay, so this completes the definition of the weak solution. Now, in order to prove that there exists a weak solution, the first thing we need to do is at least to get some a priori estimate out of it. Because if we just closely look that, okay, what we can get. So just forget this thing. What we can get from the mass balance or continuity equation, you can get that rho is over any time, is basically because it is rho naught initial data. So the only thing you can get, and since you assume that rho is always negative, so you can say rho is bounded in some L infinity L1 in space, and L infinity. But there is no other estimate. So we have to somehow exploit this ballistic energy inequality to get some estimate out of it. And this is the thing that we would like to do. So, okay, that's what I say, the total mass is conserved, at least for almost every time we get that. Now we have this ballistic energy inequality. But what is the first problem is that if we look carefully, from a structural hypothesis, we cannot say that this quantity has always a strict sign. But even strictly like non-negative in some way. But what we can say that it's, if we just add a affine function, you can make that it is always non-negative. And we already know that total mass is conserved. So if we just add this particular quantity in both sides, it will not change anything, like, because in the right-hand side, we have the same quantity from the mass balance. Therefore, we can do some sort of estimate out of it by adding this extra term. So what is the thing we do? So as we notice, this theta tilde is like any extension such that the theta tilde is theta b, the boundary data of temperature, and this is positive. Also, this is the property of theta tilde, and theta b, for the time being, we consider this is at least C2 in boundary, although people suggest that it can be removed and make something lesser. And theta b is strictly positive. So these are the only two assumptions that we have. So we considered this particular extension of theta tilde, which is the kind of an harmonic extension. So inside there is a Laplacian of theta tilde is 0, and theta tilde is taking value on theta b. So the maximum principle asserts us that theta tilde over the whole domain is actually strictly positive. And so with the help of this, the first thing what we get, we consider this term. So you see that this term is in the right-hand side. And this theta tilde now, for this particular extension, for this particular theta tilde extension, we notice that this quantity is greater than CB, and eventually this is greater than the following quantity, which is good. I will come back it later, because then we want to use something like a Poincaré or generalized Poincaré inequality in for velocity, and for temperature we get some estimate out of it directly. Next, what we do, we just want to use the right-hand side. So our goal is just to, you have this. So if we can estimate every term, this is the initial data. So this is, you can assume that this quantity initial data is bounded. And all these terms, we want to either make it like this is less than integral over time, integral over space. So our goal is just to source something like this, so that we can use eventually the Cronwall's inequality to close the estimate. So we look for these terms, this k theta, and with this particular extension theta tilde. And we notice that this quantity is basically like, you can write it some function of capital K, some K is capital, K is capital K is a function of theta, which is basically all this term we just denoted by capital theta. We use the integration by parts, and we see that only the dependence on the boundary comes to play. So only the dependence on the boundary comes to play. So therefore, this term can be estimated by some quantity only related to the boundary. And what happened to this term? Next term is, this is the most important term that we want to estimate. The first part is comparatively easier, because we know that entropy can be controlled by log rho and log theta. And whereas for this term, we know that this is greater than some gradient of log theta square, something like that. So therefore, for first term, and theta tilde is uniformly bounded, it's depending on theta tilde. So we can use some sort of like Young's inequality to get this. The most problematic term is this rho SU. And if we just separate it, so the first part, which is coming from this molecular pressure, and the second part, which is coming from the radiation pressure. So the molecular pressure is bad, but not so bad, because we know that from the third law of thermodynamics. So from here, the assumption third law is working. So we know that this script S has this particular inequality. This is taken from the book of this Perizal and Novotny. When you have this third law, you can get this extra hypothesis, and still you can control this term. And for this term, we need this extra hypothesis, which is somehow suggested that this k theta, which is, if I just recall, this is the heat conductivity coefficient. which is basically like now it's like 1 plus some theta power 6 plus epsilon, something like that. And this is some additional assumption that we have to consider in this case. So if you have this, then you can say that, okay, you can have from here, you get something like theta power some beta over 2 square. And this is actually some theta power 6 times u square, some like this. And this quantity now you can observe by some Poincare inequality, and u square can be controlled by, from this term, you get something like a gradient of u square against some Poincare inequality. So this is the main idea there. So to get that, and finally, this allows us to get, okay, this I give it for a very simple case when the transport coefficient has just 1. So I assume that u is in L2, you will have L2 W1 to L2 in time W1 space. And so finally, this allows us to get this estimate. Like, as I said, that you have this quantity. Obviously, you can make for things some function of this particular extension, since we have a very particular extension, some b theta tilde, and obviously you can add this is on right hand side also, and you get here also some a theta tilde plus rho plus b theta tilde. And so this term, now we use the Grunwald's inequality to wrap up all the estimates, and we see that in our weak formulation we prescribe that the quantities will belong with this certain regularity class, and we will achieve this regularity class from this a priori estimate what we have done. Okay, so what we have as a consequence of it, so yes. So here we state our first result. It's a joint result with Edward Fereisel. So we consider omega to be a bounded domain, and we choose, at least for simplicity, class of C3. And for the time being, I am just considering it's twice differentiable, but I would say for existence, if you only say it to be some continuous, it will be enough. So there is like some questions I came to know recently about this, is it really needed? But you see that at the end, our main goal is to also prove some sort of weak, strong uniqueness result. And there, the strong solution for the temperature, we always consider to be a C2 integrable, C2 twice continuously differentiable functions. So for that, time being, I just only consider the twice continuously differentiable functions. And such that their infima over the boundary is strictly positive. And then you always have this additional set of hypothesis of this pressure form, entropy form, the hypothesis on the transport coefficients. And obviously, we have to consider our initial data is bounded in some sense, and the external force is in L infinity. Then we say for any time t, there exists a global, like for any time to have a weak solution. So that means like we have a global in time weak solution. Okay, so this is a thing that I also want to discuss. Like if theta b is constant, you can go back to there in this case. If theta b is constant, then you may not need this extra thing, because then this Laplace, this gradient of theta will become 0. So you don't need to estimate anything. So this is like a particular case, like when you have a theta b to be constant. So there is the remark, like this condition, this additional hypothesis can be removed. And obviously also the third law, that if theta b is a positive constant or just a function which only depends on time. And here we didn't give very detailed proof, but we mainly follow the following approximation scheme that's based on the book of Fereisel and Novotny, that you do some viscous regularization of the continuity equation, then some Fedor-Galerkin approximation of the momentum equation, and some regularization of the internal energy balance. And with the similar type of a priori estimate that we have, we can again pass to the limit, and we have our standard, like the convergence method. You need to use this either for the temperature, you have to use some sort of strong convergence, and then you eventually get something, the strong convergence of density, and then pass the limit and all these things. But I must say that the next result, that's a result by Denisa Basaric, Edward Fereisel, Maria Lukashova, Hanna Mizerova, and Yun Yuan. And they give a very, I would say, nice proof on based on this penalization method. So what they do actually, just quickly say that's a very like existence proof for the problem, and it's in a very nice way. So what they do, they embed the domain into sufficiently, so you have a domain, but you embed it in a sufficiently large torus, and then you add some extra term. And we know that in torus how to solve the equation, so already solved from the Lyons-Fereisel theory. And then you add this extra two terms, like one friction term and some another term to manage the boundary term there, because you have this theta b on the boundary. So you have to, sorry, theta b on the boundary too. So you have to somehow consider something on the torus. And then you have this set of equations, this rho epsilon, u epsilon, and theta epsilon, and eventually shows that this goes to this rho u theta, which is the solution of the problem, the same problem that we try to prove here. Obviously, some additional hypothesis, some minor changes you have to assume for some theta b and everything. So this is basically gives another proof of existence for the weak solution. And now I will go to some first remarks on the weak solution. So first remark is that the weak solution should be compatible. It should satisfy. That means, like, if you consider a sufficiently smooth, weak, or even later part on the talk, I will try to talk a little bit on the more generalized solution for the from the weak solution also, which is the measure valued solution. And so even for this, a sufficiently smooth, weak, or even further generalized solution is a strong solution that we can easily check in our case. The next one is that a weak generalized or weak strong uniqueness principle. So we are not claiming anything about the uniqueness of the problem, but we claim that, okay, if you have a weak solution and a strong solution, and they're starting from the same initial data, then they must coincide as long as the strong solution exists. So at least in our problem from the Farley-Jankowski theory, we know that the strong solution at least exists for some t star, some small time interval. So our weak solution should match up to this t star. So that's the weak strong uniqueness principle says this. And that's our next result, that we say that we have the same hypothesis, but unfortunately we have to restrict ourselves in a little bit lower case, like the transport coefficient, the heat conductive coefficient is now less equal to 4. And if we have some sufficiently smooth strong solution, and they are starting from the same initial data, then we must say that the weak solution and the strong solution coincide. Okay, the proof of this is generally based on some idea which is called a relative energy functional. So to give an overview of the relative energy functional, it relates to the Bregman divergence, which is based on the very basic fact of a strictly convex function. So you have a strictly convex function E, and you then define this quantity, which is basically the first Taylor expansion in certain way, you can think. And this functional E has some sort of distance property. So you know that this U of UV is 0 whenever you have U is same as P. But if we now notice this E is somehow the energy. So if you notice in our case, we have this kinetic energy and we have the potential energy. Sorry, kinetic energy and internal energy. Unfortunately, like with these variables of rho and theta, the both quantity are not convex. We cannot say directly as a function of rho theta maps there and rho u maps there. So what is the first idea is there? We consider some variable for which this function became convex. Then we compute this Bregman divergence. And then we go back to our original old variable. So after some minor investigation, we came out to that, we write it from the conservative variable. So that means you have density, you have total entropy, and you have momentum. And if you write the total energy in these variables, then you can see that this rho times the internal energy with respect to these variables is convex. Similarly, the kinetic energy is also convex with respect to this rho and the momentum. And this is actually a direct consequence of what we assume in our first hypothesis, which is the thermodynamic stability assumption. So what we do, we compute from our this internal energy in variable rho, variable f, and we compute the Bregman divergence, and eventually we ended up in this expression. So this is the relative energy. This is the distance between the two sets of solution. And we consider some time evolution of it. Now, from this expression, from this integral expression, if we just expand, we see that it is just expansion. If you see that the quantity, it is related to the ballistic energy inequality because it's for almost every time. The second equation, it's basically, you see this, okay, for the time being, we assume only this rho theta ut and these are some smooth function. And later we will choose this particular to the strong solution. So for the time being, if you just see, so there is a rho. So this is related to the weak formulation of the continuity equation. And this is related to the weak formulation of the momentum equation. And this is some smooth quantity. So what we do, we use this thing from the weak formulation and compute it. Then I skip a lot of part, but the main idea is like after some computation, we ended up in a very crazy looking it's a bit calculation, I would say. So if you consider the initial data are same, so you get that this quantity plus some other quantities that related to the, basically this is related to the dissipation of the velocity that we have from the viscous stress tensor terms, which consider some errors like of this from like theta minus theta tilde square, some rho minus rho tilde square or something, some sort of like this. Some nice errors which we can manage from this part, because you see that as we know that from the Bregman divergence, like if this is a convex function, so somehow you can always say that at least in some part, these quantities are greater than something like this always. No, not S, but capital S, and then eventually, capital S minus S. And then eventually you can do more something on that. And it's very standard in who works in this weak strong uniqueness theory. But I am skipping this part because it's more of a very long computation in my way. But the main idea is just to prove that for almost every time you have this particular integral, this is quantity C. And then we use the convexity of the structure, and we are able to say that our desired result. That rho is basically rho tilde, u is u tilde. And this ends up, so on the proof of our result on weak strong uniqueness. Then finally, I would say that we do it for a very more general boundary conditions, which is now called also called open systems. So there, instead of homogeneous boundary condition for velocity, we consider some non-homogeneous boundary condition also, and some inflow boundary condition for the density. The similar results holds under some hypothesis, some regularity hypothesis of UB and rho. Okay, so next thing I just quickly want to say something about the measure valued solution. So if one is familiar with the like the numerical schemes of the compressible Navier Stokes system, even not for the Navier Stokes Fourier, if someone knows about the compressible Navier Stokes system, that for any numerical scheme to go to the weak solution of the compressible Navier Stokes, it requires a lot of effort, and eventually most of the schemes are not very compatible under this adiabatic exponent of like, the 3/2 or 9/5, something like this. Karpar scheme requires 3 or something. So, but it's quite easy if you see that for even for the compressible Navier Stokes system, it is very easy to show that these numerical schemes are going to a generalized solution, like the measure valued solution. So it's quite important to study this measure valued solution in this context and prove that there is a measure valued strong uniqueness result also. So if you prove that, then what we do, so you have a numerical scheme. So you have something like some rho n, theta n, and maybe un. And you say that, okay, this is going to some quantity rho, or maybe this generates some Young measure nu, which is basically a solution, a very general solution of the Navier Stokes Fourier. But this measure valued solution nu satisfies some sort of like this weak, strong, or weak, or maybe this time measure valued, weak, strong uniqueness property. So then you can say, at least on this small time, you have some sort of like, convergence, strong convergence in this small interval. So that's why we want to study the measure valued solution for this case. And if you see that in literature, it was first introduced by Diparna. And he always describes that in the order to study the weak sequential stability, and that he says that sometimes this weak limit of the weak solutions are missing. So these quantities like Young measures are basically the weak limit of the weak solution. And then Brenier, Delalis, and Sacalidis, they came up with defining measure valued solution as a general object. You don't need to consider the weak limit, but you consider as a general solution which satisfies some additional property that you need to prove. So for compressible Navier Stokes Fourier, there is always, for no flux boundary condition, there is a result by Brezina, Ferezel, and Novotny. And they provide a definition of a measure valued solution, and then came up with something like a weak measure valued strong uniqueness result also. And the last thing is basically like just to verify that what they give as a definition is somehow compatible with this kind of ballistic energy formulation or not. And I would say that we are kind of like, I am kind of like successful in that we are able to just, redo these steps, and we see that, okay, this is in measure valued setup also, it's working. So somehow this ballistic, the measure valued formulation of the ballistic energy, which is not very simple, but it somehow works there, at least in some condition. So what they do, I just briefly say maybe, sorry, how much time I have? 5 minutes?
I think, let's say 15 minutes, maybe, yeah.
Okay, fine. It will take less. Thank you. So yeah, so I would say that it's like, what I want to say here, like this, quickly, I just say that what Brezina, Ferezel, and Novotny has done, and then some minor generalization that I do in order to justify this. So their definition is very general definition, I would say, and they consider something which is called generalized Young measure. So in general, the Young measure theory always says that, okay, if you have a sequence, like in general, we know that our variables are density, temperature, and velocity. And maybe I use this maybe this notation. So some sequence like this, and they are generating a Young measure nu. But in order to have this for the Navier Stokes Fourier, they have to consider a much more general thing, which is called generalized Young measure. So instead of considering U epsilon and gradient of U epsilon as a same derivative of same function, they're considering as two different objects. So it's like U epsilon and some other quantity, which is D epsilon maybe, but they have some sort of additional relation between them. So it's a very general class of solution, but surprisingly, for even such a general solution, they are able to prove the weak strong uniqueness. So we are just quickly copy that. So what was their idea? So you know that roughly in, so you have some a sequence maybe with some uniform bound. So now you don't get this is a little bit of abuse of notation, I would say. Those it's like the barycenter with respect to this Young measure, and this is just a Young measure notation. So roughly you can just replace this mu tx of rho is by rho, and you get the same equation. So continuity equation, there is no, it's almost the same. For momentum equation, you have one extra term, and actually we don't care about this nonlinearity and the convergence there. We just, whatever we have the defect, we are just putting it in the right-hand side. So it's basically some sort of offer-determined system we are trying to solve. And then you have some total energy inequality, and roughly it's given by some defect measure. And you have entropy inequality, some weak sense, and some additional condition on this. So you see there is one defect here, another defect here. So you need some sort of compatibility condition on the defect measure, and also some additional compatibility also there. So seeing this, we just try to imitate the same thing in our case. What we do, we have the same thing. We have this continuity equation in the weak sense. We have momentum equation plus some defect, which is this one, Rm. So in weak sense, it means like this Rm times some, Rm times this gradient of phi acting on measure space and continuous space. So if you just multiply by some phi and see it and give it. So this term looks like this. I just write it in for simplicity. And also, if you see in the ballistic energy inequality, now you have another defect from dt. And also, I say you can get entropy inequality also. So you see everything, like every quantity, I just replace it by the Young measure notation. And this additional hypothesis that we get is first thing is that what I say, the defect that coming from the momentum equation is bounded by the defect that present in the ballistic energy inequality. And the next one is, sorry, this is, so this is like, you know, this, the temperature, the velocity in general are into, in some better space, even in the weak formulation level. So in this case, we are saying that, okay, it somehow also have this kind of property, but in terms of the Young measure. And we have for the temperature also, we have some sort of additional temperature compatibility, and we get some generalized Korn-Poincaré inequality in that. So it's like, it's the measure valued solution formulation with this additional hypothesis that actually one can prove if you know that there is a sequence which satisfies certain bound, you can easily prove that this additional hypothesis also will also hold. And we just what the thing we calculate in terms of the internal in terms of the relative energy inequality, we just compute the measure valued version of this relative energy functional. And just doing almost the similar step, we have these two results. The first is very simple thing, which is called the conditional measure valued strong uniqueness, which states that, okay, you have this additional hypothesis, and then you have the initial data is matching with the strong, so it should be this, sorry, it should be this. Yeah, initial data is matching with the initial data of the strong solution. And then if you assume that this initial density and density and momentum is bounded, sorry, density and temperature is somehow bounded, which then we can get that the measure valued solution is same. So it's nothing very, you know, important in the context of analysis, but sometimes in numerical analysis, it's very helpful, these conditional convergences. If you assume some additional hypothesis that from the beginning, your numerical solutions are bounded, so then it's easy to prove this kind of result directly. Or the next result, which is a much more unconditional result. But in this case, we say that instead of the standard radiation pressure of Stephen Boltzmann law, we have to consider this Latimer law, which somehow the theta square, which is not good, but in some modeling of astrophysics, this kind of form of radiation pressure comes. And for this radiation pressure, then we can prove any, we don't need any extra hypothesis in that. And this is a unconditional result that maybe we are able to prove in this case, that even if you have the same initial data and your strong solution holds some additional regularity, then the Young measure eventually becomes the Dirac mass sitting at the strong solution, and at least up to this point. So yes, this is very briefly, just I want to announce this result. This is nothing like just to check that, okay, the measure value thing is also working with this ballistic energy formulation. And here are the concluding remarks. The first, I would mention the both case has some limitation. The main limitation that if you consider that for the weak solution case, you remember the weak solution case, we proved the existence only for a very general case for that. But the weak strong uniqueness, we cannot prove up to the beta due to some structural problem. We cannot go beyond beta to be like 4. So it's better that using some other techniques or anything, if we can prove the weak strong uniqueness for general beta, it will be very nice. Otherwise, if the theta b is positive constant or it depends only on time, then yeah, we go through. And the next, in case of the measure value solution, this is also a limitation that Brezina, Ferezel, and Novotny mentioned, and we have the same that for general radiation pressure, like Stephen Boltzmann law, we cannot able to conclude the weak strong uniqueness for the measure value solution. And there is some additional current work also going on the conditional regularity of weak solution. So it's somehow related to that, okay, this is a very nice result that came from the compressible Navier Stokes equation, that if you consider that your density and your temperature to be bounded, then you can prove the regularity of the solution. So for this type of ballistic energy formulation and for Dirichlet problem, it's good to know that what will be the conditional regularity for weak solution. And okay, so there are these few references. I missed plenty of references because there are plenty of work going on this topic now, and at least also on this problem there. So, and thank you for your attention.
Thank you very much for your very interesting talk. So. Yeah, so I'm just doing this applause. So are there some questions, remarks, suggestions? I was just thinking why you need this. Maybe this is just you don't want to think about it, that you assume for this existence of weak solution for this Dirichlet boundary that you need regularity of domain C3. Maybe you can put a little bit down, no? Probably. I don't know. Maybe
yes,
not.
Yes. I think you can put it down. We just put some higher regularity just to not create any problem, because okay, we need this parabolic regularity of Laplacian somehow. So I think even C2 will be enough, I think. So yeah, maybe we just put something very smooth domain, and even that's a comment I think few people also pointed out about this theta b. I always took very high regularity. Maybe we can go down a little bit, like in certain cases.
Okay, perfect. So some questions. So it seems to be everything is very clear. No, but it is very, very interesting. So by the way, this when you have this weak strong uniqueness, this is also a big question, no? Because you have weak solution for beta greater than 6 and weak strong beta less than or equal 4. So Yeah. So.
Yes, we are not able to go for only like if you consider it's a constant temperature on the boundary, or it depends only on time, then surely you can do that. But yes, that's a drawback of this theory we are having. So, and it actually like, I think, okay, you are familiar with this thing, so you can know this better maybe. So it actually related to these computations, like you see, sorry, these terms, like these crazy terms there. And if beta is higher than 4, you cannot manage these kind of terms in that way. Sometimes I think some people, I think they sometimes, I think Yang Zhao Shun and Edward, they write for 5, but there is something there, so we cannot.
And in this paper which you mentioned with Danica and this, when they do this penalization, they also need beta greater than 6?
I think also they have some other conditions also, like theta B to be, I think, I am not sure, like time independent thing, how much they get. I think there is some restriction.
So it's necessary to have a look. Yeah, but it is interesting. Yeah, it is really interesting. Yeah, I must say. Yeah. So Sabrin, hello.
Yeah, hi.
Hello everyone. Hi.
Yeah. So you have question, no?
No, I just want to say hi to you, everyone.
Yeah. So that's very good. So,
Yes.
So we like you very much. We are missing you. Yeah.
Me too. Yeah.
Thank
you.
So
thank you, Nilas.
Yeah.
Thank you.
So it seems to be there are no any questions, any remarks. So thank you very, very much, because it was extremely interesting, extremely well prepared. I must say, very precise, really very nice. And for this year, it is last seminar, but I should say that in January, we will have, I think Outrata will give a talk. So let's say first week of January, we will have seminar. And anyway, let me wish you first wonderful Christmas with a lot of present, with no chaos, with very quiet time, I wish you quiet time to all of us. Then everything fantastic for New Year, which means health, happiness, love, simply everything which you would like to have. So I really wish you and see you next time, next year. Yeah. So.
Thank you. You too.
Bye.
Thank you so much. See you, everyone. Bye.
Oh,
Bye.
Thank you. Bye. Merry Christmas.
Bye.
Bye.